Okay, so now I want to do a video on external semantics. So basically, I want to revisit a theorem in McClarty's book, um, Theorem 18.1, which is about external semantics or Kirby-Joyle semantics. So it's basically 6 different results. I'm only going to go through the first 4 in this video because I've already done a video on this, and yeah, so basically we're supposing that we have a variable x over an object A, and we have these formulas phi and psi, which may have 3 variables in x, and we have these different results. So these, well, there's 6 of them, like I say, but we're just going to go through the first 4, and they basically tell us when the extensions of these formulas with various logical symbols in them have C in them. In other words, when C satisfies these conditions. So the first one is about and. So it says, so I mean, the picture to have in your mind is something like this, okay? We have this, well, I don't think I've drawn it for and. I should draw it. So we've got A over here. We've got this subobject of A, which is the extension over x in A of phi and psi. That's the subobject classify. So also we've got the extension of phi over x, and also the extension of psi. And so they're going to have their sub-objects classified by different things. For example, well, if we call this one B and we'll call this one A, then there's going to be a classifying arrow, chi of A, from that into omega. And what we're interested in, we have this object T with an arrow C into A. We're interested in when C is going to be in this extension of phi and psi. And so let's do this then. We're going to have C is in this extension of, well, yeah, this extension of phi and psi, if and only if doing the interpretation of this after C sends everything to true. Now, what is the interpretation of this? Well, it's interpretation of psi and interpretation of phi and interpretation of psi after C. Now, if we call A the extension of phi over x, and we call B the extension of psi over x, then the interpretation of phi we can just call chi of A, and the interpretation of psi we can just call chi of B. So this says that chi of A and chi of B of C is true. Now, we know that that's the same as saying that chi of A intersection B after C is true, which is saying that C is in A intersection B, which is saying that C is in A and C is in B. And that's basically the claim of this first point of the theorem. So we've just got the proof as well. So basically the idea is that C is in this extension of phi and psi if and only if C is in the extension of phi and C is in the extension of psi. Okay. Second result is that C is in the extension of false if and only if T is initial. So basically if C is like a kind of null arrow. Third result says that C is in the extension of phi implies psi if and only if for every arrow S from an object zeta to T, we have that C after S is in the extension of phi implies C after S is in the extension of psi. Okay. So let's go through the logic of this. C is in the extension of phi implies psi if and only if the interpretation of phi implies psi after C is setting everything to true, if and only if chi of less than or equal to of chi A of C, comma, chi B of C is true, where A and B are like this. If and only if chi A of C, comma, chi B of C is in less than or equal to, because this all comes about because the arrow here, the implies, is really just a classifying arrow of less than or equal to, and it should be lifted outside. So when we interpret this, we get this. And then to say that doing this classifying arrow on this gives true, doing this classifying arrow of less than or equal to on this gives true, is the same as saying that this is in the sub-object, that this is a classifying arrow of, as in the sub-object less than or equal to. And saying that is saying that this, like blah comma blah is in less than or equal to, is saying that, well, I mean, this is the equalizer of and P1, so it's saying that blah 1 and blah 2 equals blah 1, which is basically saying that the subobject classified by this is contained in a subobject classified by this, which is equivalent to saying that the subobject classified by this is c to the minus 1 of a, the one classified by this is c to the minus 1 of b. So this is equivalent to saying that the pullback of a along c is contained in the pullback of b along c, which is equivalent to saying that for any s from z to c, we've got that s is in c to the minus 1 of a, implies s is in c to the minus 1 of b, which is equivalent to saying that cs is in a implies cs is in b. And that's the claim. And we can see a little proof of that 1 and 2 are equivalent here. Okay, so this is the picture of what's going on. Now, an alternative way to think about this, let's write our formula with some kind of free variables in them. So these two are the same things. Now, we can sort of say what our theorem's claiming then is that this holds if and only if the extension of c tau of phi of c tau over tau in t is contained in the extension of psi c tau with tau in t. So basically, whenever we've got this c that sends stuff to make phi true, it has to send stuff to make psi true as well. So we could say from any kind of if we start from any kind of stage of definition S, and then we get C at a later stage of definition, so that would be like C after S, then whenever that satisfies phi, it has to satisfy psi. Okay. Okay, next one then is condition 4. And I must confess, I don't really understand this one fully yet. I mean, in my opinion, the easiest way to understand OR is that I've come across, that for me at the moment, is the way it's explained by Goldblatt as basically if you have omega plus omega, there's an arrow from that to omega times omega, and that arrow is t omega 1 omega comma 1 omega t omega. If you take the classifying arrow of the image of that, so you do monomorphic of it, as in you you form a corner with this arrow kind of pointing away. You could call it a co-corner, and then you take the push out of that. Then you get these two arrows. So I mean, if we call this arrow theta, let's say, then if you draw this diagram, theta, theta, and you form the push out of this. This is just how you do epimonomorphic. So let's call these things P and Q. Well then, if you get the equalizer of P and Q, then this arrow here will be the image of theta, and that's a monic. And so once you have that, if you then take the classifying arrow of that monic, that'll be I mean, basically it's isolating the pairs of truth values which have one of their entries as true. Okay, is that sub-object, and then the classifying arrow of it we can call or. Okay, so we have the or equals the classifying arrow of the image of theta. Anyway, so that's a good way to think about or, but there's this other way from the Kirk-Joyle semantics, and the claim is that C is going to be in phi or psi if and only if there exists this epic S from the coproduct of two objects, zeta 1 and zeta 2, to T, such that CSI1 is in the extension of phi and CSI2 is in the extension of psi. So we have this kind of picture. So the argument for this, I don't follow it fully, but I'll go through the parts I'll follow. There exists, so let's assume this to start with and try and show the other stuff. So suppose that C is in the extension of phi or psi. So then, because it's in it, we have this H. such that C is equal to this extension after H. Now, another important thing to notice is that this extension here, the extension of phi, is contained in the extension of phi or psi, and that's because phi implies phi or psi. I mean, see that like this. We start with the trivial sequence, and then we use the OR rule, because we know that phi or psi implies phi or psi, so we know that phi implies phi or psi. So we know that this extension is contained in this extension. So we know that there exists this monic I phi, which I subscript phi, which is kind of like showing how the extension of phi is contained in the extension of phi or psi. Okay, so that if we then pull back this I of phi along H, we get H to the minus 1 of I of phi, and we set that to be S1. Similarly, we set S2 to be H to the minus 1 of I of psi. Now, apparently H after S1, S2 is epic. And epics are stable under coproducts. These are parts of the results about stability and the back end of the fundamental theorem of topos theory that I haven't quite internalized yet. Anyway, H S1 is in I of psi. And now CS1, so I call in S1 shorthand for S after I1, okay? So HS1 is in I of psi because S1's in H to the minus 1 of I of, actually I should say phi. S1 is in H to the minus 1 of I of phi. So HS1 is in I of phi. So C after S1, which is theta after H after S1, where theta is the extension of phi or psi. So CS1 is theta H S1, which is in theta I of psi, which is the extension of phi. I keep calling it psi. I mean I of phi. So I'm saying that CS1. Right. Okay. The core thing here is this. We have HS1 is in I of phi, and that implies that theta after HS1 is in theta I of phi. In fact, we have this kind of thing in general. For example, in this case, X is in M. So we automatically get that CX is in CM. Okay, because X is in M means there exists K such that X is MK, which means that CX equals CMK. So CX is in CM. Okay, I mean, it provided you know, that might not lead to a monic in general, but I think you ought to extend the usage of this word in, even when you're not talking about things being in monics, because it's just useful notation. Anyway, by that similar kind of logic, we have HS1 is in I of phi, So we automatically get theta after h after S1 is in theta of I of phi. Now this left thing is equal to CS1 and this right thing is equal to extension of phi by the way that I of phi is defined. And similarly, we get CS2 is in the extension of psi. And that's what these are the results that we wanted, right? Now we want to go the other way around. So conversely, suppose that S equals S1, S2 is epic, and suppose that CS1 is in extension of phi and CS2 is an extension of psi. Then S1, which is S after I1, is in c to the minus 1 of extension of phi, which is contained in c to the minus 1 of extension of psi or phi. In a similar way, we get S2 is in c to the minus 1 of extension of psi or phi. Now, apparently, that implies that S is in c to the minus 1 of phi or psi. So CS is in phi or psi, and apparently that it turns out that C is actually in phi or psi. Okay, a bit of notation then. Given this arrow C from T to A, we call this arrow S from Z to T a change of stage. So CS is called C at a later stage of definition zeta. So we can think about, so we can think about sort of this S coming out of this stage of definition zeta. But then later on we do C, so we get C at a later stage of definition zeta. Now I just want to go over. So my attempt to make sense of this result about the OR is somehow it's saying that the way C sends stuff can be split into two pieces, and S1 where psi is always true and S2 where where phi is S1 where phi is always true and S2 where psi is always true. Anyway, basically in this talk of stage of definitions, our discussion of implies is basically saying that C satisfies phi implies psi if at any stage of definition C satisfies. When C satisfies phi, we have that C satisfies psi.